Welcome to today's Explainer. Today, we're diving straight into one of the most mind-bending topics in astrophysics, black holes and their absolutely massive magnetic fields. Specifically, we're tearing into the groundbreaking ATHENA Theory, which has been making some serious waves in the scientific community. To really do this justice, we're going to structure today's analysis just like a formal academic paper presentation, walking through the latest findings step by step. So if you're ready to get into the weeds of black hole dynamics, let's jump right in.
Here is our roadmap for the presentation. 1. Theoretical framework. 2. Observational data. 3. GRMHD simulations. 4. Simulation limitations. And finally, 5. Conclusion. Section 1. Theoretical framework. ATHENA predictions. Okay, let's dive into this. To really visualize the immense, complex geometry of black hole jets, we absolutely need to lock down two crucial concepts. First, we have the poloidal inflow. You can think of this as the inward pull happening right at the poles, dragging material straight down toward the center. Then we have the toroidal outflow, which is the energy being aggressively blasted outward from the equator. Now, what the ATHENA theory does so brilliantly is predict the absolute structural separation of these two massive forces.
And here is the actual mathematical engine driving that prediction. This formula right here anchors the whole ATHENA theory. It specifically models how the poloidal and toroidal fields physically break apart from one another. It's not just some abstract idea. This equation structurally demands that separation. Of course, the math is elegant, but as scientists, we always have to ask the big question. Does the actual physical universe play by these rules?
Section 2. Observational data. EHT polarization.
Well, it turns out we actually have some incredibly strong, independent astronomical data to back up ATHENA's bold claims. We're looking at the historic 2021 data from the Event Horizon Telescope, findings from the European Southern Observatory in 2023, and a whole slew of massive GRMHD simulations spanning from 2021 all the way to 2026. It is genuinely fascinating because all of these independent cutting-edge studies are converging on the exact same phenomenon.
Now, what's really interesting about this is the polarization data from the Event Horizon Telescope. It shows a distinct clockwise spiral pattern right at the jet base. Why is that such a big deal? Because that clear clockwise spiral is physical proof. It demonstrates exactly how the toroidal magnetic field at the equator completely dominates the poloidal component. We are literally watching the theoretical math come to life out there in deep space.
Section 3. GRMHD simulations. Structuring the jet.
Let's look at what our supercomputer General Relativistic Magnetohydrodynamic or GRMHD simulations reveal about the dynamics of the jet. They cleanly separate the jobs of these two fields. The toroidal field is dominant at the base of the jet, and its primary role is keeping that jet narrow and stable. It's almost like a giant cosmic corset squeezing it tight. On the flip side, the poloidal flow is what actually organizes the outward bursts, and crucially, it acts as the main carrier for all that massive energy. So right here, these simulations are giving us the direct observational counterpart to ATHENA's predictions.
Section 4. Simulation limitations. Evaluating the gaps. Now, any rigorous academic review has to look at the weak spots, right? And there are definitely some methodological gaps here. Even our most advanced standard GRMHD simulations are still built entirely within the traditional boundaries of general relativity, which means they're giving us mostly qualitative data. The big missing piece is quantitative separation. Put simply, because of the foundational biases in how these models are built, they don't actively or quantitatively test the ATHENA alternative with hard math. So we're in this weird spot where deep space observations persistently point directly to ATHENA, but our computer simulations are still somewhat stuck in older paradigms.
Section 5. Conclusion. Strong theoretical agreement.
So, pulling all of this together into our final takeaway, despite the methodological flaws and the undeniable gaps in our current simulation models, there is a remarkably strong agreement between the real-world data we're gathering and the ATHENA predictions. Between those spiral traces captured by the EHT and the narrow, elongated structure of the jets themselves, the evidence indisputably confirms that poloidal flows and toroidal fields separate perfectly exactly as the theory outlines.
Which brings us to one final, incredibly provocative question. Observations clearly support ATHENA, but when will our simulations finally move beyond standard relativity to test it quantitatively? When is the scientific modeling going to catch up to the reality we're already seeing in the dark stretches of space? That's the boundary we need to push next. Thank you so much for joining me for this explainer and for pushing the complex boundaries of science with me. Stay curious.